All right, so let's do another example. Let's go ahead and solve a circuit, but we're going to use KCL this time. So I'm going to go ahead and draw my circuit with my sinusoidal source here. We're going to call this Vs of t. And this time I'm going to put a resistor here, and then I will put a capacitor right here, another resistor right here. All right, that's my circuit. I'm going to call this R1, this will be C1, and this will be R2. Okay, so what I'm going to do here, again, is I'm going to give the parameters for this problem. So kind of just how I did last time, let's go with R1 first, and let's just say that it's 500 ohms. You could write it as 0.5K too if you would like. Let's say that R2 is going to be 200 ohms, and let's say C1 is 1 microfarad capacitor. Let's say that we're operating at a frequency of 100 hertz, and let's say that our sine wave amplitude, Vs, is, let's just say, 80 volts, okay? So similarly, let me go ahead and put a box around these values and kind of move them out of the way. And then I'll label some nodes here. Let's call the first node, let's just call it Vs, and then we'll call this other node Vx. And what I want to determine in this circuit is what is Vx of t. Okay, that's the problem. We're going to ask find the voltage Vx of t basically, okay? So let's just move my circuit parameters kind of up and out of the way again. And let's go ahead and start by writing out Vs of t, which in this case is going to be 80 times the sine of omega t. I'm just going to write omega t. I think we know now that omega is 2 pi f, so I don't need to write it. I guess I could. In this case, it's just 100, so it'll just be 200 pi t volts, right? 2 pi times 100 times t. So that's my Vs of t. If I really wanted to, I could go straight and write the phasor, which I can write as 80 angle 0 volts, right? Hopefully that makes sense now. That's pretty straightforward. And I want to determine Vx of t, right? That's what I'm going for. Okay, so let's go ahead and do that. What we notice about this circuit, hopefully, is that we can use KCL. But first, we have to get this circuit into the impedance and phasor domain, where we write the impedances instead of the resistances and the capacitances, right? So let's go ahead and do that. And draw it just like this, our circuit. All right. And so my capacitance, ZC1, obviously ZR2 is just going to be 200 ohms. ZR1 is just going to be 500 ohms. 500 ohms. And then my capacitor we're going to have to solve for, because we know that the impedance of a capacitor is 1 over j omega c, or minus j over omega c, which in this case is going to be, let me go ahead and just calculate that, 1 divided by 2 pi times omega times f, which is 100, times c, which is 10 to the minus 6. And I get 1591.5. So my impedance of my capacitor is actually minus j 1591.5. Okay, so I could write that here, but I'm just going to conserve space and just note that that's what ZC1 is. I just solved for it, okay? And so now hopefully you recognize, of course this is my phasor Vs, that I can use KCL at this node. I've got a current that's going to flow into this node, and then I've got two currents that are going to break out of that node, sort of. I can call them I1, I2, and I3 if I really want to, but we could also just go right for writing the equation. The equations, of course, this is Vs of t, this is Vx of t, but we're in the phasor domain, so let's just keep it as VS and VX for now, capital VS and capital VX. All right, there's a lot more math to do, but this video is probably getting pretty long already, and I don't want it to be too long. So let me go ahead now that this problem is set up with KCL. Actually, the last thing I'll write here is, of course, we know that I1 is going to be equal to I2 plus I3. And so now that we have that, we can pretty much solve this problem. I'm going to go ahead and end the video, and in the next video, we'll go ahead and finish this problem up. All right.